Hello everyone, in today's class we're going to go through some examples on chapter 3 regarding conduction heat transfer. We're going to continue on from the last lecture where we covered the overall heat transfer coefficient and we went through the meaning of it and how it's calculated. In today's class we're going to start with an example. Okay, so the example we have is a fridge that has an insulator as a door. This is the door of the fridge acting as an insulator to stop temperature from leaving. Okay, we're asked to draw the circuit of this system here, and we're also asked to find the heat flux. Now, let's focus first on the surface, and we can see that this here is the inside of the fridge. There's convection happening. The temperature is lower inside than outside. Okay, there's two insulating materials here. One is the steel plates on the ends of the door, and in between these steel plates is a insulating material. Okay, now let's go ahead and start drawing this thermal circuit. But before we start, we need to know which way the direction of the heat is flowing. So usually the heat flows from the hotter area to the colder area. So in this case, we're going to be calculating or drawing our thermal circuit from the right side to the left side, because heat always transfers from higher temperatures to lower temperatures. So we're trying to see how much heat is actually transferring through this insulation, and if this insulation is effective or not. Okay, so we're going to start with our thermal circuit. So we're solving for A. The thermal circuit first starts, the first temperature knot is the outer surrounding temperature. Okay, which is this here. Then the heat flow goes through the first insulator. It goes after through the second insulator. Sorry, it goes through the first steel plate. It goes then again through the insulator, and then again through the second steel plate, and then the heat enters the inner side of the fridge. So starting off with the first temperature, the outer surrounding temperature, that goes through. Some of that temperature is lost to the convection resistance. I'll say convection 1, or the outer convection. Okay. It then goes, some of that temperature is also lost to the second steel plate, first steel plate through conduction, which is this here. Okay. Then some of that temperature is lost to the insulator through conduction. That's conduction for insulator. Again, some of that heat is lost to the second steel plate through conduction. Steel plate 2. This is steel plate 1. Steel plate 1. And then finally, some of it is lost to the inner convection, which is inside the fridge. Second convection. This is first convection. Okay? And your final surrounding temperature is T infinity I, which is the inner surrounding temperature. So that right there is our thermal circuit for this system here. Now after we have found the thermal circuit, we can start by solving for the heat flux. We can start by first solving for Q, which is the heat transfer. Heat transfer equals change in temperature divided by the resistance. Now the change in temperature, the difference in temperature, is the outer surrounding temperature minus the inner surrounding temperature divided by the sum of all the resistances. So that will be R convection 1 plus R conduction of the first steel plate plus R conduction of the insulator plus the R conduction of the second steel plate plus R convection, which is the second convection, or we can call it the inner. We can call this the inner, and that will be the outer convection. Okay, now we need to write these terms, the value of these terms. So R convection of the outer side will equal to 1 over the outer heat coefficient times the area, and the R conduction of the first steel plate will equal to the length of the steel plate divided by the thermal conductivity of the plate plus the area, which is similar to our conduction of the second steel plate, because they both have the same length and they have the same material, therefore having the same thermal conductivity and the same area. Okay, now the R of the insulator, the resistance of the insulator, which equals to the length of the insulator divided by the thermal conductivity of the insulator times the area. Okay, and the final resistance is the resistance of the convection in the inner side of the fridge, which equals to 1 over HIA. Now we can substitute these values into our equation, and we can solve for Q. We know that the heat flux equals the heat transfer over area. Therefore, heat flux equals 1 over A times the value of Q we have found here, which is, the outer surrounding temperature minus the inner surrounding temperature divided by 1 over H naught A plus 1 over initial HIA plus LP over KPA plus the same term again, or we can just times it by 2 to save time, but I just added it again, plus, which other one am I missing? The insulator. the resistance of the insulator, which is Li divided by KI AI. Okay, and that is our heat flux, the equation for the heat flux. Now we can multiply this area inside here, therefore we'll get heat flux equals to, these areas will cancel. Okay, this area, it's not an insulator area. Okay, these areas will cancel. We'll end up with heat flux equals T infinity naught minus T infinity I over 1 over HO plus 1 over HI plus LP KPA. No, the A's cancel. Okay. Plus Li over Ki plus LP over KP. This has a value of 0.2. You can double check. These two have a value of 0.00005, and the insulator has a value of 1.5, which shows that the insulator has a higher resistance than the steel plates. Okay, I think this could be misinterpreted. So I will say that each one of these will equal to this value here. This, copy and paste. Not the total of these two terms, but each term has a value of 0.00005. Okay? Just to avoid any confusion. And this term here has a value of 0.2. Okay? Therefore, the heat flux will equal to 14.14 watts per meter square. And that's it for this example. But the main trick was understanding which way the heat is flowing, because I've seen some students start their thermal circuit from this side to that side, which was the default way of solving previously. But this example here was a trick to see which way you will start. You should always start from the higher temperature to the lower temperature, because heat always transfers from high temperatures to lower temperatures. That's it for today's class. See you in the next one.